Demetri Psaltis. Electrical engineering, I guess by training. And he became a professor at Caltech for over 20 years. And later moved on to EPFL since 2007, where he's now the Dean of School of Engineering. And also a professor of bioengineering and director of the Optics Lab. He's known for optical computing, holographic storage, and neural networks, which will, I think, some parts of all these things will explain to us in this talk today. He's well known as one of the founders of the field optofluidics, which is the coupling between fluidics and optics. He actually had the wiki page, which I just found out and didn't know about. So you can find out more about him on that page. And we're honored to have him kick off the first 3 keynote talks. And this talk is titled Teaching Optical Systems by Example. Let's welcome Demetri.
Thank you, Dwayne, and thanks also to George for inviting me here. This is my first time at Singapore. It's a fascinating country. I live in Switzerland now, and people say it's Switzerland and Singapore have similarities in terms of, wealthy small nations of highly organized, and really it seems wonderful. Yeah, so thanks for the introduction too. I haven't been dean anymore it's been more than a year now that I have not been dean, which is, but that's the professor there. So today I'll talk about teaching optical systems by example. What I mean by that is normally if you have an optical system, you try to understand its operation by the physics of it, the physical operation of the system, and try to design it and use it based on this understanding. More recently, learning techniques in general have been adopted in many domains where you present examples and then from the examples then you try to without really understanding the underlying physics perhaps, to try to operate the system. So the idea is to use the same approach in optical system design and operation. So let me see, yeah. So in my career, I've had 3 opportunities to apply this concept. One is an old one. This optical neural networks goes back, I don't know, 30-some years, which the idea is to build a physical optical system that is adaptable and it can change in response to training, and build an optical neural network in hardware, in optical hardware. So I'll tell you a little bit about that. And then more recently, we've been working on multi-mode fibers as imaging devices instead of lenses or other imaging elements. And then again, we train those by presenting examples and then using the examples to convert a multi-mode fiber into an imaging element. And then the last topic is learning tomography. And I think I have an hour or so, right? I still have an hour. So in an attempt to try to unify these 3 concepts, I have to back off a little bit here. I made this diagram. So basically, the way I can integrate all 3 concepts in this or projects in the same talk is to think about an optical system. This could have lenses, holograms, gratings, scattering media, whatever. And then there's some incident illumination, which can be controlled with spatial light modulators. So you can think of this as the input or the illumination to the system. Then the light propagates through the optical system, gets scattered, modulated, and some of it gets captured by detectors and measured, and some of it escapes and doesn't get measured. And that's the system. So we have ways to specify the illumination, ways to detect some of the scattered light, and the medium, which is characterized by the 3-dimensional complex index of refraction of this medium. So this is the lenses or anything else. So notation-wise, and hopefully I'll follow it throughout the talk, the input illumination is a vector F. So the vector is the different pixels on the SLM. Each element of the vector is a pixel. The same thing for the detector is G. It's a pixel on the detector is an element of this vector. And the operator that operates on the input and gives us the output is H, capital H. If this system is linear, then the output is simply a matrix H times a vector F. If it's nonlinear, oh shoot. If it's nonlinear, then it's just an operator. So these are the 4 elements. And the 3 examples that I'll talk to you about is how do we learn H? In other words, if this is an adaptive optical system, has elements in it that can change in response to a training, we use the training set, pairs of inputs and outputs with some operator H. We use this training set to specify the optical system. And then the other 2 I'll get to as we go forward. So this first topic is something I worked in a long time ago when I started my career at Caltech. Actually, this got me tenure at Caltech. So the idea there was we have neurons or pixels on an input plane, what I called F before. And then the output plane is the next layer of neurons. And these planes would be interconnected by optical elements, typically gratings or holograms, or volume hologram. So a light beam originating from a pixel here gets collimated by a lens. So this collimated beam then gets diffracted by this grating in a direction that when focused by this lens goes into an output pixel there. So this volume gratings could store to the order of 1 billion gratings or so, or maybe even more. So you can collect large arrays of neural planes here to neural planes there. And then the nonlinearity that's necessary for neural networks is done by optoelectronic devices which detect the light and then perform some nonlinearity and then re-emit it on the other side. So you have these multi-layer networks. So at the time, this was the beginning of neural networks. This is approximately 1990 or late 80s. So I'll describe to you one of the systems we did then, which was, in my mind, the most interesting one. So it was a face recognition system. So we had a VCR at the time. The VCR would record a few minutes of a video of a person moving around. And so during the training phase, we would take the video from the VCR, and then we would modulate the holograms that were constituting the neural network. Then by presenting the faces on a liquid crystal display, probably similar to what's here. So that was extracted from a projector. Then the training would modulate this first layer of the network. And the second layer was an electronic layer. So in the middle, there was a detector array, and the output was the network. Let me see. OK, so here's a little more detail of this network. So the input phase would go here. There was some spatial filtering to edge enhance the images. Then the hologram, which is something called a photorefractive crystal, would take this input image and then connect it to this array of a detector array of about 1,000 elements in the output plane. And the training would happen by having this mirror rotate such that with the light from this mirror would be focused on one of these detector elements. So if you present one face here, then we would train a unit so that the light scattered from this hologram would produce a strong response to that unit. So this training or this reinforcement would happen only if the response was not hard enough. In other words, let's say we wanted one unit here to be recognized young. This guy is named Young. In other words, the light here to be strong. So if by presenting this image here, we got a strong light there, and at the same time we had enough units turned on in this detector array, we would do nothing. But if either of these two conditions wasn't true, if there were not enough units on and this particular unit was not strong enough, then we would turn on the reference beam and record a hologram to reinforce that. And then repeat that. Present thousands of frames here and repeat it. As a result, what would happen here is a representation that was distributed. For each version of the young face, there would be many, many responses here, and this response is shown here. So, and then this responses then would be integrated by the second layer into a single output and connected to an LED. So if this was recognized as young, this LED would turn on. And this is okay. This is some of the results. This is the output of the detector, the final unit, showing the response for the training set. This is in seconds, so the training set was about a minute or so of young moving around, and then the response would change. Then and again, while this training set was presented, actually often multiple times, these units would continuously be updated. Then when Young was presented the different instances of himself, this is the response that we got. And then when two other people, this is Sid and Alan, not shown, were presented, this is the response that we got. So the idea then is to put a threshold here, somewhere in the middle, and get to recognize Young and not the other two guys. And this is some examples. If you change the illumination, that didn't work so well. But, or if you took just part of the face, it didn't work so well. But most of the time it worked quite well. So this statistically, the probability of error, this is 1. And then when you pick the threshold optimally, the probability of error is about 10% on a single frame basis, so just capturing one frame. And then if you're willing to look at the person in real time for 6 seconds, and the probability of error went down to 0. Okay, so this was, I don't know, I got this new iPhone X, which has this face recognition thing now. So that's been a big change. But this is, remember, this was done back in 1986. So, you know, we're doing real-time face recognition in 1986. So this got a lot of attention at the time. But, and the way we justified it, it was at the time we have about 1 million pixels at the input, 1,000 hidden units, which means a total of 30 billion synapses per second, which would be very difficult to do at the time, even with custom hardware. But nevertheless, this did not translate into a commercial product, or for various reasons, primarily because there were so many things happening in neural networks on the software side and the digital hardware side that didn't have time to do it. So if you look at, this was the paper, one of the papers you published at the time, which was cited nicely. Like I said, this thing got me tenure. So we got a lot of citations. This is 1990. But then by the late 90s, it trickled down. So a lot of excitement, but no lasting impact. Here I misquoted. If you look more recently, this has taken off again. So a lot of people are citing it again. And the reason is because there's a lot of activity once again. This is a book published by Personal at Columbia, Neuromorphic Photonics. This is George's place, MIT News. New system allows optical deep learning. And this is the one I like the best, by Marin Soljakic, who is a colleague of George's at MIT. He's a very smart guy, a friend of mine, who has this published this paper in Nature Photonics about how to build a neural network using photonics. A lot of the ideas that people like this are talking about now are similar to what we were talking about then. You know, you have optical neurons that do some nonlinearity, and you have optical interconnections between the neurons. And the advantage is the connectivity of optics and all of that. So that makes me, you know, makes me feel good. All the stuff we did back then, somehow it's coming back. So it's fantastic. And, you know, they cite us and all that. They do have a couple of things that are different that I think will give this time a better chance. One is they use silicon photonics. They don't use this three-dimensional architecture. Everything is done in silicon photonics and in the plane. And then it's done in the context of big databases. As you may know, the silicon photonics has had a big infusion into big data centers. So big data centers, optical interconnects is being used quite a bit. So you have already an existing installed base of photonics for interconnects. And since neural networks are expected to be used widely for searches in these big databases, the idea is that to do it optically in an existing optical interconnect network. And Marin here makes a very good argument that doing it with photonics, it would be much more power efficient, which is an argument we also used to make back then, because you don't have to charge capacitance lines to do a weight. You just have to have light transmission through a waveguide. Okay, so this was my first exposure or my first encounter with trying to use learning, meaning trying to use a training set to try to specify what this optical system does. In this Young recognizer, you would put Young here and you configure the hologram so that you get a strong response here when Young was present and not somebody else. The next example I'll show you is a little bit different, where we still are trying to use the training set to learn this operator from input to output, H, but we don't learn that on the optical system, we learn that in the computer. Meaning we take the examples F and H and we try to understand what is the transfer, and we use that information, for example, to invert the system. If I put an input here and I get an output there, if I can estimate this operator, I can invert it perhaps and do inverse scattering and find what the input is. Alternatively, I can do wavefront shaping. If I want a desired output, sorry about this. If I want a desired output here, I can pre-calculate it and put something there so that I can program it to present the right output there. So the example or the project we worked on was to take multimode fibers and find a way to present on a special light modulator data so that when you put it into the one end, into the proximal end of the multimode fiber, the light as it propagates and gets dispersed with the different modes propagating in the fiber. By the time it gets to the other end, it gives us a focused image. So let's say I want to project some specific image here. If I know this operator H, I can figure out what to put on the SLM here so that the right image will appear on the other side. The motivation for this is to have this, instead of having a microscope objective like this, which you cannot insert into tight places like the body or small cavities and so forth, maybe you can have a very thin multimode fiber like this. That's like a needle that can be inserted in fine places, and then in the far end, you can form the image and then convey it back to the operator. So single mode fibers are widely used in communications, as you probably know. So if you put a Gaussian-like beam, a single mode beam on the one side, this will propagate unperturbed to the other end, and you'll get this Gaussian beam outside. In a multimode fiber, if you do the same, if you focus the light on one end of it, light will be coupled into many, many modes, and they will propagate in different phase velocities. So at the end, these different modes will interfere with one another, and what you will see on the other end is a speckle pattern. That's not related to anything that you put here. So it looks like a mess for imaging purposes because it distorts the image. For example, here, if you put EPFL on the proximal end, on the near end, and you let it propagate for some distance, which is not that much, this is a tenth of a meter, then you get total speckle looking. So this is not this is a distortion, not a loss of information. In other words, the different modes that make up the image EPFL, as they propagate, similar to diffraction in free space in the multimode fiber, they become blurred, distorted, but the information is still there and can be recovered. And this is why we can do this. We can use this as an imaging device. It turns out that this is an old idea. A fellow, actually somebody I know well, Eric Spitch, he's retired now, in 1967 did this experiment. He took a multimode fiber, and if you try to transmit an image through it, you get a speckle pattern. But if instead you transmit that speckle pattern, you make a hologram of it, in that case, a holographic plate, 649F, for those of you that know what that is. What we used to make holograms a long time ago. Then what Eric did, if you illuminate the hologram from the backside, you get what we now call phase conjugate reconstruction. At the time, they didn't call it phase conjugate reconstruction. But basically, it's like a time reverse or a phase conjugated wave that goes backwards and then enters the multimode waveguide, and all the damage that's done because of the distortion of the modal dispersion in the fiber gets undone, and you get the focused image back. So that's what he did in 1967. So if you will, this is a way of presenting one example in the hologram and storing it in the hologram. And so this one example and its response stored in the hologram basically trains the fiber to be able to transmit this one image back through the fiber. So what I'll show you that now with modern technology, it's possible to transmit any image through the fiber, and through any fiber, by the way. So it's kind of by having multiple examples. But the basic idea was done back then, by Alan Spitz. Then Yariv had a very nice paper about how to transmit images through fibers. Basically, he was using two matched multimode fiber segments, trying to have one undo the scattering of the other. This did not, again, it was a nice idea, but did not become practical. So more recently, there's been a flurry of activity, literally hundreds of papers trying to use multimode fibers as imaging devices. And of course, we are part of this effort. I'll tell you about our work, as usual. Okay, so the idea is this. The goal here is to take a multimode fiber and produce a focus spot on it on this end. So to do that, you illuminate it just like Spitz did with a pattern on this side. So you take a focus beam, you illuminate the fiber. Then that beam is coupled into multiple fibers and produces multiple modes and produces a speckle pattern. This is the speckle pattern. The speckle pattern is holographically recorded on a camera. So you can see, this is what it looks like. You can see the fringes because the reference beam introduces an interference pattern. So in the amplitude and the phase of this interference pattern is encoded the complex field of the pattern. From that, we extract the phase. The phase then is put on an SLM down here. And then the light is then goes back into the fiber. And what you see here is, oops, let me see. Something's not right. But anyhow, what you are seeing here is the evolution of this. Let me try it one more time. I don't know why it does this, but what this movie does is it shows you as a function of time what happens to the beam as it propagates from here to there. So it starts as a speckle pattern. As it propagates, it comes to a focus. So it's supposed to end by being in a focus. I don't know why it does it. But anyhow, then so once you have it focused, what you have done is record it in the computer. You go in the computer, the memory that allows you to focus in one spot. Then what you can do is repeat the experiment by focusing this beam in different places here in the facet and recording the corresponding phase patterns. So that now you have in the memory of the computer multiple phase patterns corresponding to multiple positions at the output. So we do this for roughly 100,000 spots. So that's easy to store in the computer. Then by presenting each of these 100,000 spots, you can choose where to focus the beam. So I don't know if this will work now. Okay, what you see now is the scanning. And this is done by electronically playing back these stored patterns onto the SLM. So this is done at the proximal end, and the distal end the beam scans. Again, normally you would have to have a MEMS mirror or some other scanning mechanisms in the far end to do this, but this now is done all electronically. And this shows an image obtained of a stained neuron So the neuron is placed here and it's fluorescent, so when light focuses on it, fluorescence is generated, and that fluorescence is gathered back to the same fiber and detected on the camera. And then as the beam scans, you form the fluorescence image. So this is fluorescence image obtained through the multimode fiber, and this is the same neuron image through a microscope objective of the same numerical aperture, and you get very similar performance. The resolution in this case is about 800 nanometers. So the idea here was to have a scanning microscope, instead of using an objective lens, using a thin probe, so you can get performance similar to the objective, but however with a better form factor. Now, if you want to transmit an image through this fiber instead, you can think of I hate this. Okay, I'll try to be. You can think of putting a point source here and recording the speckle pattern on the other side as a way of recording the impulse response of this linear system. The system is not shift invariant, it's shift variant. In other words, the response changes as I move the input on this side of the fiber. But nevertheless, since I'm willing to repeat this 100,000 times and record 100,000 responses on the computer, I can have the full impulse response of the fiber, which means if I want to synthesize an image, let's say consisting of 2 spots, what I can do is take the 2 phase patterns corresponding to the 2 spots, add them in the computer, have this sum then presented to the SLM, and if I play it backwards, because this is a linear system, each one of them, the sum will be represented as the sum of 2, and I can produce an image of the 2 spots. If instead I want to have an arbitrary image, what works for 2 spots works for 1,000,000 spots. So I can have a linear combination of any of these phase patterns corresponding to the response of the individual spots in the fiber, and project an arbitrary image in this way. Instead of using input delta functions to characterize the system, I can instead do the spatial frequency response. I can present different frequency components, which practically means different plane waves at different illumination angles. And then by changing the angle of illumination and recording in each case the corresponding frequency response, if I want now to present an arbitrary image, I can take each of its frequency components, map it to the corresponding speckle pattern corresponding to the frequency component, sum them all up, put them on the SLM. Again, the sum is done digitally on the computer, but you present it on the SLM, and then when you project that back through, you get again the linear combination of the frequency components, all the right phase and so forth, and you get the image reconstruction. So one of our students, Damien Loterie, made a movie of that by taking a movie and taking each of the frames, mapping it into the speckle patterns corresponding to propagating through the fiber. And then he projected those images on the other side of the fiber. And now, let me see if I can play this. Something happened when I... This is a movie, but I can't play it because I transferred it from my... we transferred it from... it's on a stick now, so it's not on my computer, but... But this is a movie of a cartoon showing this each of the frame now have been encoded into the frequency response of the fiber and then played back through the fiber. I suspect that none of the movies I have will work, but anyway, believe me, this is a movie, and then it happens through a fiber that's about 600 microns in diameter, which means if this fiber was on this wall, it would be a little speck on this wall, but then I could project it so that the movie would play on the wall across the room. And of course, I can have many of these fibers all over the room and maybe create an interesting display system. Let me see if this will play also. Yeah, I have a problem because none of these movies will play because now because somehow I couldn't connect the computer. But one of the problems with these fibers is that what we train them to do. So right now, this fiber initially was something that as imaging device was useless. But once you train it by presenting these examples, now you have full control of it. You can project images on the other side. You can project spots and scan them. You can predict what the image would be, what the image would be on the other side by detecting the speckle pattern on the proximal end and so forth. However, it has a problem that if you bend it, then you have to retrain it, because what you learned for a particular configuration of the fiber it will be different for a bent fiber, because when you stretch the fiber around, the modes, the phase delay through the modes changes. And this video was showing a way to correct that by having a virtual beacon. So, but by transmitting through a single mode fiber onto a hologram on the far end, a signal which gets reflected back through this multi-mode fiber, and there's a virtual point source that forms on the far end, and you can use this virtual point source to continuously correct. And this movie shows the focus spot flickering on and off as we bend it, and then with this compensation turned on, this spot stays.
Sorry, maybe we can try to play the movies. I asked the tech person.
Oh, okay.
Maybe, do you want to take like a 2-minute break? See if we can.
Maybe I cannot do it with this. Yeah, I see. Okay, I see. I have to do it with the mouse, not this guy. Okay, I can do that. No problem.
I think that's a play.
But I described this already, so you can see what happens, right? Thank you very much. Yeah, it's very good. Actually, I'll take the opportunity and show you the other movie. Maybe this will play now too. Again, this was a movie that was encoded in the each frequency component through the speckle pattern of the fiber, and then put all back together and play through the fiber. There's an audio, but it doesn't matter. Yeah. So this movie goes on and on. So it's a lot of data, right? But so each of these frames is encoded to 100,000 frequency responses, but it's nothing on the computer. Okay, so I'll skip this part, other than to say that we can also do the same thing that I've been showing you with CW. We can also do the same thing with femtosecond pulses, basically by using the dispersion of the fiber to train each delay separately. And you can do really interesting things, because as you put a femtosecond pulse here and it disperses, then at each time slot here you can encode a different transformation. So you can imagine having like a very fast movie playing on this end, spatially, because each time slot would get a different spatial transformation. But I just want to show you one example of what we've done recently here is you can do 3D printing through a multi-mode fiber, which could be interesting, because if you want to 3D print in tight spaces, if you're making complex objects, and 3D printing generally requires 2-photon polymerization, which means you need the femtosecond pulse. So this is the fiber put in a container, and then it has photoresist, which then photopolymerizes, and then the whole apparatus is pulled upwards. So basically, the multimode fiber scans the spot here, just like I showed you before, in one plane. Then that one layer of material is polymerized, solidifies, then it's pulled up a bit, and the next layer is polymerized, and so forth. And this way you can construct a structure here. Right? So this is in a small little beaker. And here's one of the things, the student working on this, Edgar Morales, he's from Mexico, so he built this little pyramid. And again, the thing to notice here is 10 microns. This is a 10 micron spot. So the whole thing is very, very small. The resolution is sub-micron of the construction. So you can do ablation, of course, imaging, and so forth through these multimodal fibers. So in this part of the fibers, I want to acknowledge Yanis Papadopoulos, who's now in Berlin, who did a lot of the early work. Also Nico Stasio, Damien for this movie, and Edgar for the femtosecond. Okay, so now I come to the last part, which is also the most perhaps interesting or difficult part. Darn. Again, I have an optical system here, which is not adaptable. It will not change, but I still have a training set of input and output. And the task here is not to find the transfer function or the function that takes me from F to G, but instead to characterize the medium itself, to find out what the index distribution is, which is a much more difficult task than finding the input-output relations. So I still have an illumination pattern, a detected field. And detected could be either complex amplitude with holographic recording here or intensity. But H could be linear or nonlinear. But the key is to be able to characterize what the medium is. In the context of the multimodal fiber I was just talking about, the difference would be, if I have this fiber here, what we did before was to take the examples from input to output and use them to find what H is, which would allow me to, specify what I could put here so I would get a desired output there, right, or vice versa. Given an output here, I could tell you what the input was. Now, the task would be, given a fiber, to characterize it, what it looks like. I would put inputs here, I would get some spectral patterns out here, and I would need to use these pairs now to characterize what the fiber is. And this is a nonlinear problem to get from this G back to N. And the reason it's a nonlinear problem is easy to see in a sense, because suppose I double the index here. In other words, I have a certain index, some core and cladding. And suppose I increase that, I double it, then the modes will change. Because I will have a higher core index, and so I will have different modes with different phase velocities. So the spackle pattern would change. For a linear system, it wouldn't change. It would just get twice as big, strong. So this is a very nonlinear problem, normally. So the output is linear in input-output, in this case. The system is linear in input-output, but not in index to measured output. So this is a kind of a, with Colin in the audience here, this is a three-dimensional imaging problem. How do you, and many techniques exist for that, including confocal microscopy or two-photon microscopy. But the one we focus on is tomography, but it applies to all the other things as well. So in tomography, just briefly, okay, this is, it also doesn't play. Let's see now if I can make it play with this. I don't know why it doesn't play, but okay, let me see. Now what? Okay, I'll tell you what happens. I won't play it then. So let's say this is a cell. This is a sample we want to image. This is the index distribution we would like to estimate. And now we think of this as a three-dimensional inverse scattering problem. So it's a cell with a nucleus, and it's illuminated at a particular angle, and we see that projection. If the thing played, you would see this beam change in angle, and as it changes in angle, the projection changes a little bit. The nucleus moves in different directions. And from that information, we want to recreate what the index of distribution is of this object. So this is, of course, done in X-rays, X-ray tomography, where there's no diffraction. But in optics, there is diffraction, so this is the typical setup. So you have a laser, which in a Mach-Zehnder configuration, part of the beam comes and illuminates the object at a certain angle. and then that interferes with the reference on the camera, and then this mirror is rotated to create different angles to illuminate this object. So this way I've accumulated a number of measurements, and I think of this as examples. So the training set is like this. So I have different measurements here and different illuminations. This could be different angles, it could be different patterns, whatever. So these pairs of different illuminations and different detection schemes is recorded, and from that we're going to go back and reconstruct what the three-dimensional index distribution is. So this is the reconstruction tomography problem. So the traditional approach, or the way to do this, in X-rays is the Radon transform, but with diffraction we use the Wolf transform, which is a method described by Wolf. So if we have the 3D distribution here, and then illuminate it with a plane wave, then this plane wave will see, if we think of this 3D distribution as a superposition of three-dimensional gratings, a little bit like the volume hologram I showed you before. So each of these gratings diffracts the input plane wave to another plane wave. The lens focuses onto a pixel. So now, by measuring light in a particular location on this pixel, knowing the location of the pixel tells us, and knowing the incident angle of illumination, we know everything about this grating's orientation and frequency. So we know which frequency component. There's a one-to-one mapping from the frequency components here to pixels on the camera. The strength of this focused light tells us the strength of this beam. So this is done simultaneously for every time we illuminate it with the plane wave. This is done simultaneously for the number of pixels we have on the camera, which is typically several million. And then we can, by changing the angle, we have a whole set of different frequency components. So the Wolf transform says that when I illuminate a three-dimensional object with a plane wave, and I look at the projection on a camera, basically what I'm doing is measuring a subset of the frequency components of the 3D Fourier transform of the object. So I accumulate those, and then I do an inverse Fourier transform, and this is how I reconstruct the image. So this works reasonably well. It has two problems. First of all, generally it's not possible, it's not comfortable, convenient at least, to image this from all different directions so that you can access all the different frequency components. That's one thing. So that's referred to as the missing cone problem. And then the other problem is it ignores multiple scattering. In other words, it assumes that each photon detected on the camera here was scattered only once by this object. So by a photon that arrives, originates from the laser and illuminates the object, it assumes that it's scattered only once by this grating. In reality, this plane wave, as it comes into the object, if the object is thick enough, it will be distorted before it gets rescattered by the back end of the object. So this is multiple scattering. So this multiple scattering is not accounted for in this Wolf transform kind of thing. And multiple scattering translates to nonlinear system. So in other words, if this incident beam gets scattered again here, formally we say that the scattered light that's measured on the camera is related to the index of refraction. This is the scattering cross-section, but this is related to the index of refraction. It's a function of position. The incident light and the scattered light again, because the light that's scattered inside the 3D object gets rescattered within the object, and then it reaches the detector. So this multiple scattering, if you try to invert the system, is a nonlinear inversion. So the input-output relationship between the input illumination and the detection is still a linear transformation, but the relationship between the detected signal and the index of refraction here becomes nonlinear, unless you're willing to neglect the scattering inside the object, which is called the Born approximation. So if you don't apply the Born approximation, the system is nonlinear. So there's been a lot of effort to try to correct for that. And our approach has been the following. We have the measurements. This is actually real data. By changing the angle of, okay, this is playing, so I'll leave well enough alone. But this is also a movie. And as the angle, what you see here is this angle changes. this thing we saw different projections. So this is the nucleus, some different elements in the cell. This is a HeLa cell, a type of cancer cell. And then what you see here is a model describing how, a computational model describing how light propagates through this. So the idea would be to have the measurements here. So this is what I've been calling G. These are the G's, and the prediction of this model for what the light should look like at the end of this sample, and compare the two. And if the two are not similar, then correct my model so that the two match. So this model will contain as parameters the index of refraction of the medium, and we'll do it this way. So this says the same thing in equation. These are the measurements, and this is the input illuminations, plane waves or other fields. And this is the model which describes how an input illumination gets mapped to a measured field. And this transformation depends on the index of refraction of the cell in this case, or whatever else. So what we do is create an error signal. If there's a difference between the two of them, we're not happy, so we have to find an index distribution that will make the two be closer. And we want to minimize the error over all possible indexes of refraction. And if we, in fact, achieve this, if we find an index of refraction that makes this 0, then we found this perfect solution. But normally we don't. But this offers an opportunity as well in this minimization process to add other things like positivity, because we know the index of refraction is positive, sparsity, whatever else we know about the object, to put it in so that we can create images. So now the question is, what do we use for this nonlinear forward propagator? So in what I'll show you, we use a beam propagation method. So you take this cell, this three-dimensional index distribution you're trying to estimate, and you slice it up into little prosciutto slices, little salami slices. Each slice is a very thin phase object. So as you have an input beam like coming through it, what happens as you propagate through a slice is two things. One is you have a phase modulation because of this thin slice. Again, this is unknown. This is the one that we're trying to determine. And then because of the finite thickness, you have a little bit of a diffraction, Fresnel diffraction through this thin layer. So as we propagate through the object, slice by slice, we can calculate the full diffracted field through the object one bit at a time. This model does not account for reflections in what I'll show you. In what we're working now, we also account for single reflection, but in what I'll show you now, no reflections. This is redrawing what I've showed you before in a diagram to make it look like a neural network, even though it's not a neural network, but it looks like a neural network, which means it can be trained like a neural network. So you have the incident field. This is what I've been calling F. Then in each layer, you have the phase modulation because of the thin slice of the phase object. Then the black lines is a fixed diffraction. These are weights corresponding to the Fresnel kernel elements. So then this repeats again. Then the next slice gets modulated by the phase and Fresnel diffraction. And then we go through the entire phase object. And then we get to the output, which is, this is what I've been calling G. And the measurement then is compared to the prediction and create an error signal. And the error signal, just like a neural network then, can be used to correct the unknown parameters, which are not the weights of between the neurons as in the conventional neural networks. It's instead the phase modulations at each of these nodes. These are fixed weights on the other hand. Input-output, this neural network is, this network, I shouldn't call it neural network, but this network is linear from here to there. But of course, the relationship between the thing on the nodes and the output is nonlinear, as I just talked about. So the training, again, is error backpropagation. So this is what we get. So again, just to repeat, you run the experiment, you collect typically for about between 20 and 100 projections, 100 holograms, put it in the computer. And now you set up this network I just showed you with these unknown parameters at the nodes, which describe in 3D the index of refraction of the object. And you start iterating. And then in this red curve, the initial condition was the reconstruction from a tomographic direct inversion algorithm, and then the horizontal axis is iteration number. As time goes on, the error goes down. The vertical axis is the error gets diminished, and then you reach a plateau and you stop. So this is the initial iteration. This is what the direct inversion gives. And then after iterations, you have this evolution, and at least visually you have a lot of improvement and a lot more detail showing. And then the error goes on as well. Even more remarkably, I think, if you start with nothing, if you start with a constant index of refraction change compared to the background analyte, or water basically, so no other information, it starts iterating, and even from the first iteration you start seeing something, and then it converges to the same signal. Okay, so this is some more data from this. So we call this learning tomography because, again, we use examples. So this is learning tomography. This is a radon transform, doesn't take account diffraction. And this is diffraction tomography. This is Wolf transform I showed you before. So with 81 projections, 81 different angles of illumination. So this is what I showed you before, the plane, and this is diffraction tomography. So you can see, again, a visible improvement. What's most interesting, I think, here, this is 81 projections. When we reduce the projections from 81 just to 6 projections, diffraction tomography gets blurred, which makes sense because, as I said, as I tried to describe before, each angle of illumination gives you a subset of frequencies in the 3D Fourier transform space. So if you take now some of these illuminations away, you have a smaller part of the 3D spectrum. So it's as if you're low-pass filtering the image. So this is what this blurring is. But here it doesn't. So just with 6 projections, you get an image that's practically the equal quality. So the question is why? Why does this work like that? And one answer is because this is looking for some sort of minimum in the error function. A minimum where the index of refraction that is discovered and the forward model, the beam propagation model projection based on this index distribution matches the measurements. So if that happens, you get a small error. And that's it. So as long as you can find this minimum, you don't have to have all the frequency components measured. In all of this is additional constraints, which I didn't really describe. These additional sparsity constraints are very important because this is without sparsity and with sparsity. So you can see the improvement. It's not only because of the learning process, but it's also these additional constraints that you put into this. I think I have about 5 minutes left. So now I'd like to, the next thing I want to do is talk about a little bit about how much improvement can we expect by this learning approach compared to the direct inversion approaches like the Wolf transform. And to do this, it's always difficult in any learning problem. What is the ground truth? How do you know what the cell is supposed to really look like? Maybe you know, who's going to tell you that? So we've done work on with particular kinds of objects, like very symmetric objects, like spheres and cylinders. You can have full closed form solutions based on, or computational solutions based on Maxwell's equations. It's called misscattering. So with misscattering, you can predict exactly if you illuminate the object with a plane wave, so this would be the F, what the G will be anywhere in space. And then you can rotate the input just like that, and have for free this ground truths. So you can generate samples for free in symmetric objects. So that's nice. So then so now this makes it easy to compare. Let's say if we do this with direct inversion, this is what we call linear because it's been linearized. You neglect the multiple scattering versus this learning. So these are 3 cylinders that are sticking out in, you know, this is X and this is Z, and the Y is in and out of the surface of this projecting surface. So these are 3 cylinders, and then light would be coming from left to right along the z direction. So in this case, the reconstruction of the linear and the nonlinear, or the Wolf transform and this learning tomography, are the same, because here light propagates through one of the cylinders and then doesn't meet the other. You don't have the multiple scattering problem. But as you completely rotate this arrangement, so the 3 cylinders are stacked in Z, light comes through the first one, then gets distorted by the first one, hits the second one, and so forth. So the direct reconstruction methods assume that each of these cylinders sees a plane wave throughout, because single scattering means the plane wave is approximately not distorted as it illuminates this, or any other illumination pattern. And this causes this distortion. And distortion is multifold. The shape, the size also not shown here, and then this other artifacts. Whereas this learning approach can deal with that because, again, it calculates the distortion of the field as you propagate. Now this is experimental with 2 beats. This is a z-axis, so this is 2 beats, one after the other. And it shows similar things as the simulation. So these are 2 beams, 2 beads that were equal diameter, but the reconstruction of the linear or the direct method shows one bead overestimating its index of refraction and then underestimating its size. This is xz, and then this is the 2 xy, cross sections of these 2 beads. Where again, this nonlinear beam propagation method with this iterative shows a much more accurate response. Now, if you do it now with cells, this is a yeast cell, not a HeLa cell like I showed you before. Again, for cells, we don't have ground truth, so we don't really know what it really looks like. But you can have confidence. So this is, for the linear case, for the Wolf transform, this is the reconstruction you get for a single cell. So for a single cell, you would expect the Wolf transform to work relatively well because these are very low index of refraction, so the plane wave is not distorted. But still, you see additional features, additional organelles inside the cell that you don't see in with the linear scattering. If we put 2 cells, one after the other, you see very similar behavior like we saw with the 2 beads. So the 2 cells, one after the other, if you see, this is the xz, this is the propagation direction. You see these artifacts in the middle, again, because the first cell distorts the beam and the second cell cannot deal with that. And you see in the cross-section, in the xy cross-section, you see almost no features inside the cell. Or once again, here you can see features inside both cells. So this is once again a movie. Let me see if I can make it play. So this is our most recent result. So what I showed you before with 2 cells, in all tomography work that I know, diffraction tomography, it's all been done on a single cell. I think there's never been one reconstruction of a tomographic image with even 2 cells, let alone tissue. So again, the problem being, again, because you have to assume that the incident plane wave is not distorted by the front part of the sample. So this learning approach, or the beam propagation approach, can deal with that because of the scattering. And so the 2 cells work very well. The question is, how well does it work with thicker samples? Can we do tissue? Can we look inside tissue? And what I show here is a sample we prepared by putting, again, yeast cells in agar and creating a 3D sample where cells are being suspended. So, and then what you saw here is making the 3D reconstruction of this whole sample and then digitally rotating it around. And if you look carefully, in most places, there's 5 or 6 cells. So being able to see through 5 or 6 cells, which is a significant improvement. Okay, this brings me, so in this part, it's a collaboration with Unzer, but I'd like to to talk about Juwon Lim, who's my current student, who did all this me work stuff, and then Ulukbek and Yanis, who started the work on the tomography that I showed you in the early part. So yeah, so I like to finish with an advertisement that, so this is a very rich area. You can do so many things because you can detect intensity, you can put wavelength, you can put polarization, you can change the illumination pattern. There's so many ways to explore different things about learning. So there's many projects, many opportunities for graduate students and postdocs. So I have a lot of projects that I like to work on. So we're looking for students always, but you know, there's more ample supply. But definitely I would like to have I'm looking for a postdoc. So if any of you are interested, then go to our website and take a look at how to apply. So I'll stop here and take any questions. Yeah.
I mean, it must be because the multiple scattering is giving you information about additional spatial frequencies, right? In order to make that error minimum, it has to know something about how all these other modes are getting propagated. Is that your?
Okay, that's a very. I mean, you bring up a good point. That's different than.
If you didn't have multiple scattering, it wouldn't work. You need it.
Okay, the multiple scattering can give you super resolution, just like structured illumination super resolution. The same idea, right? They use structured illumination, creates new frequencies that now sneak into the numerical aperture. So some of this happens, yes. But even without that, I think you can recover resolution because the system, the virtual system in the computer operates at higher resolution. Right? You know, the sampling grid in the computer operates at high resolution, both Z and X and Y. And it's looking for an index distribution that will best match the measurement. So if it finds it, then the error will be very small. So, yeah, but what you say is also true, that you can get some sort of super resolution in the structured illumination sense, that frequency components that wouldn't be there through multiple scattering. So that's a very interesting topic, but I think it's secondary really to the other, because multiple scattering is weak, in particular in cells, which are very low index contrast. So, but it's a valid point, you know, it's a valid point to see.
So what about uniqueness, though?
I'm not answering to you. I'm sorry. What? Uniqueness? Sorry, go ahead. I was just kidding. Say, uniqueness. Or how do you know it's a unique global minimum?
Well, there could be
local minimum
different refractive index distributions
that give you absolutely. This is a very good point. Because now for the nonlinear, because it's a nonlinear problem, it's not a convex optimization problem. It means if you look at the energy landscape, it'll be all over. So we see this a lot, particularly in this the last thing I showed, in the multiple. There's a lot of local minima. So you have to do everything you can, like stochastic descent, add noise in the system to try to get out of it. And eventually you can't, you get stuck. And something else I didn't have time to mention, there's also this business of phase wrapping. As you get to very thick, because you have to measure phase. As you get to very thick samples, you go over 2 pi, and for a while the learning corrects for that, because phase wrapping for the learning approach is another local minimum. So then you get some phase contrast, which sometimes it gets undone, sometimes it doesn't get undone. And yes, so as it gets complicated, you have this local minima, you get stuck there. So, and that's the that's the true limitation of this approach. Now, how do you get rid of it is by getting more data, is my opinion. In other words, if you now, in addition to have spatial diversity, means different illumination examples, if you also include wavelength diversity, if you include different ways to introduce more data, then hopefully you can find better ways to, or better initial conditions, by the way. It's always good to have good initial condition. or to have the direct inversion method give you something close to an object. Yeah.
Yeah. When you do the salami slicing in your learning algorithm, so what is the thickness of the salami slice? You hit the depth of field of the microscope.
Yeah, he can predict, knowing the numerical aperture of the lenses that you have in the system, you can predict the expected delta Z, the resolution in Z. And if you know the numerical aperture of the lenses, there's a direct relationship with it's like the depth of focus, but for tomography. So then we normally use 4 times less than that. If we did things perfectly, we expect a resolution, let's say, of 1 micron. So we usually slice it to 250 nanometers.
So then, next.
Did you understand? Did I?
Yeah, I know it. But so how do you deal with low frequency components? For example, if you propagate to smaller slices than the depth of focus, how do you know that, for example, low frequency contents are not just in the first slice because they're not affected by the Fédérale propagator much? How do you mix them out? Do you have some mechanism in it, or do you just compare, or how does it work?
Well, the low frequency components are the easy ones because you just integrate the phase across it. Let's say if you have, in this beam propagation method, we have low frequency components. As the plane wave comes through, it's just like a phase integral. The diffraction is little. So they are covered because the phase measures more or less the optical path. As you go to spatial modulation, high frequency component spatial modulation, then you start getting diffraction from slice to slice. Are you familiar with radon transform?
Yeah.
If it's very low frequency components, then you might as well use a radon transform. Doesn't matter, right? You don't have to use this diffraction stuff. Because
Comes to the uniqueness argument, because you could put the low frequency components anywhere in these slices. It doesn't matter. It's for the Fédérale propagator. It doesn't care where it is. It's not sensitive to the low frequency component.
But for the Fédérale propagator, if they're very low frequencies, the Fédérale propagator will not do much. Right? Because low frequencies do not diffract very much. But they're there. And they manifest themselves as phase delay of the incident beam.
I know. Okay. Maybe we can discuss it later.
Yeah. But obviously I'm not conveying, but the low frequency
Artifacts from low phase parts that appear, they can be, if the part in one plane and get the opposite part in the next plane, so they move between the planes because there's no way the Fédérale propagator is stopping them.
they will move when they accumulate. Yeah, they will accumulate. But I think they're there. I don't think they're missing. I mean, there are frequency components that may be missing, but this is more of the high end.
I think we're getting to technical deep water, so let's leave that for lunch. Let's thank Demetri again for